Carmenes, the importance of being complete. Since I am talking on Carmenes and we are in San Diego, I must do it. Carmenes, San Diego. Okay. Now, Carmenes, yes. Of course, yes, it is an acronym. The CAA, Calar Alto, that's an observatory in the south of Spain and the mainland, not in the Canary Islands, okay? In Spain, in the south. The last S is spectrograph, so it is not transit, it is radio velocity. And then in the middle, you have high resolution, 80,000 in the near infrared, 96,000 in the visual. That means that it has two channels in the spectrographs and in one shot covers from 0.5 microns to 1.7 microns without gaps. Main aim to look for planets of terrestrial Earth mass around M dwarfs. Carmenes is the name of the instrument, the name of the German-Spanish consortium that built the instrument, of which I am very proud because I was the project manager, and it represents the best of the Germans and the Spanish. The Spanish engineering and the German passion, or reverse, both, believe me. And Carmenes is also the name of the scientific project that has been carried out during warranty time observations and then afterwards during legacy. And we have published something like 80 planets, around 70 during the GTO and legacy time. One of them is this one. Well, actually there are two. T-Garden star around the second lowest mass star is T-Garden B is the planet with the greatest Earth similarity index according to Arecibo, and recently we have published a third paper in the system by Dreisler et al. 2024. So we just here at 3.5 parsecs we may have an system similar to TRAPPIST. This is the kind of objects that we were looking for when we built Carmenes. We were lucky because NASA launched tests, and we have discovered a number of transiting planets that have a mass determination at less than 10 parsecs. This is one of them, and this was so important that was one of the first targets of James Webb, and even received a name by the International Astronomical Union. And then you can see there Carmenes compared with Maroon X Gemini, more or less the same radio velocity precision at about 1 meter per second. And then at the bottom, TESS and Cheops. And we complemented this work with XMM Newton, Hubble, Chara, and a lot of small telescopes. With Carmenes also, we have discovered other things for which it was not designed. For example, we discovered from the ground the famous helium-1 line of transiting planets with which we can model the atmospheres of planets and objects or systems that were a surprise, such as this one, which is a Jupiter mass planet around a 0.1 solar mass late M dwarf, which it is a challenge for formation scenarios. This is our updated plot in XY stellar mass. In vertical, we have the planet mass. Red and blue are either only Carmenes or Carmenes and TESS. And as you can see, below 0.5 solar masses, half of the detections have been done with Carmenes. Have I been clear? Yes. That reminds me to a plenary talk that I gave in Uppsala in 2016, and I show exactly these slides. I was talking about Carmen Theta, the Carmen's input catalog of bright nearby stars. And Carmen Theta is not the first movie with sound that it is in the US library, nor what the Spaniards add to our paellas, but the Carmen's input, Carmen's Cool Dwarf Information Data Archive, from which we identified the best targets for the radial velocity follow-up. Initially, we started thinking of monitoring with radial velocity around 300 targets, but eventually they were a few more. I have updated this slide. This slide with respect to Uppsala. That was the top part is a copy of all the compilation that we did before 2015, and at the bottom there was a thanks to all the people who had been in Cool Star 17. So now I have updated. I have to say thanks to those of you from which we stole your M-dwarfs, and then Adam is here, Celine is there, Dave is here, Eric is there, Gibor is there, Hugh is listening, Jackie is in there, good. Julio Jonquis he's listening, Jonathan Gagné, he gave a talk, Sebastian, Todd. Okay, we had an input catalog of 2,200 M-dwarfs. We started preparing this 6 years before Gaia, which means that we could not make a volume limited sample, but it looks like to it. It is just choosing the brightest objects within each bin of a spectral type. And in the end, you have a catalog of bright nearby M-dwarfs. Here, red means the input catalog of 2,200. Blue, the final target list of 300. Average magnitude, 7.7 magnitudes in J. Nearby, mean distance, 11.6 parsecs. And of course, M-dwarfs, mean spectral type around M3 with a mode at M4, but a long tail up to M9. Those 2,200 stars, for them, we have compiled during many years a lot of parameters. Since Cool Stars, we have included, of course, a lot new parameters derived by us or measured by Gaia. And I will mention a few because the Carmen's team is very large. Alonso Floriano spectroscopy, Cortes Contreras Lucky imaging, Jeffers activity, Reiner's Bison eye radial velocities magnetic fields, Fürmeister activity, all the lines that you can think of from 0.5 to 1.7 microns, Baroque et al., the spectroscopic binaries, including the white dwarf that has been presented just before, Diez Alonso photometric periods, Passeger, TF, log G, metallicities, Hint activity indices, Schweitzer, masses and radius, Schäfer, more activity indices, Schuljak, more magnetic fields, Avia, vanadium abundances, Cifuentes, magnitudes, colors, luminosities, Lafarga, more activities and more radial velocities, Marfil, TF log G metallicity, Perdelvich activity in H and K, Shan, that was vanadium before it was strontium, Newton-Shan vanadium and more photometric periods, and Bello Garcia, more astrophysical parameters with machine learning. 3 minutes. The importance of being complete. Ours is not volume limited. So what Carmenes can do? First, we are limited by the observability from Almeria, which means that we cannot observe below declination minus 23 degrees. And we are also limited by the size of the telescope, which is 3.5 meter telescope, which means that we are limited by magnitude. But I checked our input catalog for this meeting, and there are 294 camera theta M-dwarfs at less than 12 parsecs. Of them, we have monitored them 177, which leaves 117 without the radio velocity monitoring. That is because 84 have close companions at less than 5 seconds, including spectroscopic binaries, astrometric binaries, and close companions that you can think of, which means that there are only 30 stars at less than 12 parsecs that we have not monitored with radio velocity and without companions at less than 5 parsecs. One of them is at less than 9 parsecs, and that is the name, so you can monitor it, but I think that we should do it with Carmenes. In the south, Spirou. In the middle, Espresso, Hubs and Hubs North. This is not only Carmenes. Everybody should be doing this. Final, 7 tips exoplanets are nearby stars. This sentence has been said several times here. If you don't know the star, you don't know the planet. Nearby, how much nearby? I have heard something like nearby 250 parsecs. No, man, this is not nearby. This definition of nearby is for making the things useful for the next generations. And for me, I think that whatever volume limited sample must be useful for what is the big science nest. They are Plato, they are Andes at the extremely large telescope, but especially for NASA Habitable Worlds Observatory and ESA's Large Interferometer for Exoplanets. What it is expected to do, what is missing? Really, multiplicity. Catherine has talked about this and many others. There are a lot of still hidden systems in our sample at less than 25 parsecs, more than you think. The multiplicity fraction, it is more than 30% in M-dwarfs. Just remember, we are on shoulders of giants. Some giants are sitting down here. And there are many catalogs in the web, so do not think that zero, including star names. So if the star name is LSPM whatever, use that name, not TOI whatever. Repetition is not always bad, and please quality instead of quantity. And the last thing, is stellar activity a showstopper? It may be. Thank you very much. Questions? Ricky. Yeah. Ricky, it's okay.
Can I have the first question though, Ricky? Oh, thank you. Thank you so much. So, thanks, Jose. That's great. I was there at the start when you first presented Carmen Theta, and we were all super excited about it at that time. So I think it's amazing work you've done. My question is, on average, how many epochs does each target have, and what is the cadence? Like, what do we expect from?
You mean radio velocity observations?
Yeah, like how many multiple observations do you get of it?
Rivas et al. Published a paper. Sorry. Yes. How many observations, radio velocity observations we have per target? Last year, we made public 20,000 spectra, multiplied by 2 because there are 2 channels for the 360 M-dwarfs, which means an average of about 40 measurements per target, but it is because we still have a few that we have not completed, and they have of the order of 20. We stop in general the monitoring when we reach 50, but there are some stars that have more than 100 visits and some radio velocity stars that have more than 700 visits. All those data are public. Just write Carmen SDR1 and you can retrieve them.
Time for one more question.
Yeah, it's working. No?
Tragically Edinburgh. Can you talk about biasing against binaries? I assume your input list must have had some binaries in it that you hate, probably threw away. Talk a little bit about that process.
Yes. The easy answer is 5 arcseconds. We discarded everything that had a companion at less than 5 arcseconds. At more than 5 arcseconds, we kept it, except for just 2 cases, because the companion at 6 or 7 parsec was a very bright star, naked eye star. So at less than 5 arcseconds, we discarded everything. In the end, it resulted to be very good because we had a contamination of only 12 spectroscopic binaries, which were published by Baroque, and those of them were the white dwarf that were presented before. That was just because there was not a radio velocity monitoring before. But this is something that if we want to invest time of habitable worlds observatory, that must be done for sure in advance from the ground.
Okay, let's thank our speaker again. Okay, so can you hear me better this time?
I'm doing it. Yeah.
How about now?
Hello.
Okay, it's my immense pleasure to be
Okay, good.
able to introduce Tom Nickel.